Okay, it isn't difficult to get a little broader perspective than the textbook gives you, and it makes it easier to follow some of the reasoning in the textbook. They give only a short paragraph related to the gradient of a potential function and so forth. So just to put it in a little broader context, the book does tell you that the gradient of u, there's del u, the del operator, which I'll explain in a second, of u, is simply you take the partial derivative of u with respect to x multiplied by the I vector, partial of u with respect to y multiplied by the j vector, partial of u with respect to z multiplied by the k vector. And let me back up. If you want more information, I can try to get my entire 40 hours of multivariable calculus lectures up on the internet, something I need to do anyway. It's going to take some time to do that, put it up on YouTube, and you could have reference to those, I could give you references to those parts that discuss these things in more detail. Since you're taking multivariable calculus, a little more information about how these concepts apply to physics, which are in my course, might be useful, depending what the emphasis of the course you're presently taking might be. And believe me, I'm not saying that your course should be the same as my course. My course is from my perspective, and your course makes its own decisions about what should be included and what shouldn't. In any case, that's the expression that you have in your book. U is the potential function. Now, what's a partial derivative? The book doesn't tell you what a partial derivative is. I don't think. I didn't look at that closely. I just looked up under gradient and saw where it was introduced and so forth. Well, partial derivative is a simple idea. Again, the motivation for it and how it's related to the physics. I'm not going to talk about that right now because you don't really need it. If you're taking multivariable calculus, you should develop that intuition if you're going to be an engineer. Okay, so the partial of u with respect to x, for example, means the derivative of u with respect to x in which you take all other variables to be constant. Okay, so if you're doing a partial of u with respect to x and you've got y's and z's in your function, you just treat those like you would any other constant. Now, when you take the partial with respect to y, pretty clearly you're going to treat x and z as constants. And with z, you're going to treat x and y as constants. And you're going to just take the derivative using the rules that you already know for taking derivatives. Okay, now the del operator, it's a convenient idea. You have a del operator. That operator we could write as partial with respect to x times I plus partial with respect to y times j plus partial with respect to z times k, so that when this operator is applied to a function u, okay, you just apply this to u, meaning you do partial with respect to x times I of u, which means a partial of u with respect to x times I, and this gives you the partial of u with respect to y times j, and this gives you the partial of u with respect to z times k. That's your del operator, and the del operator is very important. You use it to define the gradient, you use it to define the divergence, you use it to define the curl, which are extremely important topics in more advanced physics classes, and you might as well kind of get used to the notation here and get your feet wet with the idea if you have the time and if you're on top of your multivariable calculus and other courses. This is something you might just want to keep in mind as you go through your multivariable calculus course, and you'll experience these, you'll encounter these things, and you'll encounter divergence and curl and gradient. Okay, what we have here is the gradient. Okay, that's the gradient. The del operator applied to u. Now, we have the characteristic of conservative fields that a field f is conservative if and only if there exists a function u such that f is the gradient of u. Okay? It's one of the conditions given in your book, I believe. And you have the other equivalent conditions. For example, the integral around any closed path is 0. If f is a gradient of a function u, then it's easy enough to prove that around any closed path the line integral is 0, the line integral of f dot delta s, which could be interpreted as the work done in moving around the curve by the force f. Now, to prove that general thing, you need the techniques of multivariable calculus, and I could easily do that, but we're not going to go that deep into the multivariable calculus because it's not prerequisite for this course. But then the question of, is f equal to xi a conservative field? And I'm going to say yes without telling you how I got this, and then I'll tell you how we can get this, okay? So the answer is yes, and that's because f is the gradient of u for the function u equal 1/2 x squared. It's easy to verify that if u equals 1/2 x squared, you get the gradient of u, the del dot u, is equal to xi. Okay? And how do we do that? I'll let you fill in a couple of the blanks, but what's the partial of u with respect to x is what? Well, it's x. Okay, partial u with respect to x, use 1/2 x squared, is clearly x. You know how to take these derivatives, that's really obvious. Okay? And what's uy? So that you have a partial u with respect to y times j. Well, uy is just 0 because the derivative of x with respect to y is 0, and uz is 0, so that the gradient of the u function is just xi plus 0j plus 0k, and that's just xi. Now, we'll go on in a subsequent video to show you how you would get this, but it's basically just finding the right antiderivatives. Okay, an antiderivative of x is 1/2 x squared, and that's why this potential function gives you this gradient, or this gradient.